All right, thank you for joining us today. And in this video, we are going to find the nth derivative of what? Some functions. So we have started Leibniz Theorem, and we are thinking about how to differentiate this one to the nth term. So we are going to take the nth derivative of some functions here, and then we start with Leibniz Rule, right? So that's what we are going to do here. So, for example, if we have this function y is equal to a to the power bx, we want to find the nth derivative. So how are you going to do that? Now, for us to find the nth derivative, this is like we having our vin, right? So we need to differentiate it and look at the pattern, and then we try to write its nth derivative. So that's what we are going to do. So since we have y is equal to a to the power bx, then when we are differentiating this, what will be y1, right? So y1 is going to be, we have a to the power bx. So when I want to differentiate this one, we can see that the base here is constant. So I'm going to have something like a to the power bx times, then I'll differentiate the top, which will be b times ln of the base. This is how I did it. Maintain the function because the base is constant. I'll do derivatives so you understand how I did this. Since the base is constant, maintain the function, which is here, multiply it by the derivative of the top times ln of the base. So that's what we are going to have. So this is going to give us b times ln a times. So that will be the first derivative. Let's talk about the second derivative again. Y2 will be equal to, now don't forget, everything here is constant. Can you see that? Everything here is constant. So and the only thing that we are going to differentiate is this, which we have done it before. And when we did it, we had this function right here. You see that? Yes. So when we are differentiating this, we are going to just maintain this one. We are going to write this one here and rewrite this one again. So we are going to have b times ln a times, then when we are coming to differentiate this, and when we differentiate this, we are going to have this. So we are going to have a b x times b times ln a, and this is going to give us b squared times ln a squared times that. Let's do the last one, then we can look at the pattern. So y3 will be equal to the same idea. I will maintain the whole of what is here and just differentiate this. So I'm going to have b squared times ln a squared times. Then we have already differentiated this and we saw that it's supposed to be this. So I'll rewrite again abx times b times ln a. And then when I do that, I'm going to have b to the power 3 ln a to the power 3 times b to the power a to the power this. Now let's look at the pattern and try to write the nth derivative. So one thing that we can see is, look at this one, look at the y1. We can see that we have a to the power bx, a to the power bx, a to the power bx throughout. So it is not changing, right? Then we can see that we have b ln a, b ln a, b ln a. But what we can see is, you can see that this one is like to the power 1, this one too is to the power 1, which is corresponding with the number of times we are differentiating the function. Look at this one, this is 2, this is 2, which is also corresponding to the number of times we are differentiating the function. This is 3, this is 3, also corresponding to this one. So the nth derivative will be b to the power n ln a to the power n times a to the power bx. So as we saw that this is not changing, this is not changing, this is not changing. But when you pick the ln, the power here is the same as what is here. When you pick the b, the power here is also the same thing. When you come here to, this one is the same as this, and this one is also the same as this. So the nth derivative should be this going with this, and then this also going to do this and maintaining this one. So this will be the nth derivative of this function, right? Good. Let's pick another one. Let's look at this where we have a length function and we want to find the nth derivative. So y is equal to minus ln of x. So what will be y1? Now what you need to know is when you want to differentiate a length function, let me just bring the minus here. A length function is 1 divided by what is inside the parenthesis, which is this, then times the derivative of what is inside the parenthesis. So what is inside the parenthesis is x. So times x derivative. So the prime there means I'm differentiating the one in the bracket. So y1 will be minus 1 over x. Then when I differentiate x, I'll get 1. So y1 is equal to minus 1 over x, which is the same as minus x to the power minus 1. So that's what I'm going to get. So now we can now follow the pattern to do the differentiation. What will be y2? When I'm using the power rule, minus 1 will drop, come and multiply the minus, giving us positive, then we subtract 1. So we are going to have negative 2, right? So negative 1 will drop, making this positive. We subtract 1. 1 minus 1 is minus 2. And this is the same as 1 divided by x squared. What will be y3? y3 power rule, minus 1, minus 2 drop, we subtract 1. So we are going to have minus 2x to the power minus 3, which is the same as minus 2 divided by x to the power 3. What will be y4? So some of the functions, you need to differentiate it like 6 times, 5 times before you can even see the pattern, right? Then this one, minus 3 will come and multiply minus 2, giving us 6. Then I'll subtract minus 1 from here. So we are going to have minus 4, which is the same as 6 divided by x to the power 4. Let's go again. X to the power x5 will be minus 4 will multiply the 6, giving us minus 24. X to the power minus 5, which will be minus 24 divided by x to the power 5, right? So here now we can try to find the nth derivative. So let's look at the function. So one thing that we saw from the differentiation is, starting from here, is we have plus, minus, plus, minus, plus, minus. So we have alternating, positive and negative. So in math, we can use the minus 1 to cover for the minus and then the positive. But let's see how we can do it. You see, since I have minus 1 here, I need to check what is here. When it is 1, what happens? When it is 1, I have negative. When it is 2, I have positive. And you know that negative 1 to the power 2 will give us positive, right? Will give us positive. Then negative 1 to the power 1 will give us what? Negative. So negative n to the power 4 was also giving us 4. So it means that the power that we are having is going to be, when it is 1, we are going to get 1. When it is 2, we are going to have 2. When it is 3, we are going to have 3. When it is 4, 4. So it means that when it is n, we are going to have n. So we are done taking care of the minus aspect, right? The next thing that we need to do is we need to look at the denominator, right? So the first derivative, we saw that this is x to the power what? 1. This is the x to the power 2, x to the power 3, x to the power 4, x to the power 5. And they were going with the number of times we differentiate. This one 2 is 4, this one is 3, this one is 3, 2, 2, 1, 1. So it means that if this one is n, then we are going to have this one to be, let me say, x to the power minus n, right? That's what we are going to have. I mean, if I'm using this one, then I need to divide it by x to the power n. right? But it's the same as writing it this way because it's the same as this one here. So x, this is 5, this is minus 5. This is 4, this is minus 4. So this one is n, this should be minus n. Or I can delete this one and divide it by x to the power n, which is also the same thing. So we have taken care of the minus 2, but we can see something here too as well. When we differentiated the function for the first time, we had this one to be 1, right? We had this one to be 1. We had this one to be 2, 6, 24. So what kind of the thing that we can see here? Here, because of the number of the way we are doing that, this one will go with factorial, right? So now let's look at the y1. The y1 is 1. The y2 is also 1. Y3 is 2. Y4 is 4. And y5 is 24. We are picking the what is left, right? So now what can we see? We want to write it in the factorial form, right? So we can see that if I have 3, for me to get 2, then I need to have 3 minus 1. 3 minus 1 will give me 2, right? Here too, since I have 2, 2 minus 1 will give me 1, right? And here, since I have 1, I will say 1 minus 0 will give me 1. But because we want to use factorial, it will be 1 minus 1. So that 1 minus 1 will be 0, and then 0 factorial will be, 1. So this one will be 0 factorial, what is 1? And this one will be like, we have something like 2 minus 1 factorial, right? Let me shift this one small so that we can do it and see it very well. Good. Let me put it here. Good. So this is what I'm trying to mean. Now I have 1. So 1 can be written as 1 minus 1 factorial. This can be written as 2 minus 1 factorial. This is the same as 3 minus 1 factorial. This is the same as 4 minus 1 factorial. This is the same as 5 minus 1 factorial. What is 1 minus 1 factorial? 1 minus 1 factorial is like 0 factorial, which is equal to 1. This is like 1 factorial, which is also equal to 1. So you see that we have the 1, 1, right? This is like 2 factorial, which is equal to 2, which is also here. This is like 3 factorial, which is equal to 6. And this is like 4 factorial, which is equal to 24, right? So now let's look at how we wrote the factorial. You can see we see 1, 1, 1, 1, 1, constant throughout. Then we can see 1, 2, 3, 4, 5 also going, with the idea that this is 1, this is 1, this is 2, this is 2, this is 3, this is 3, this is 4, this is also 4, this is 5, this is also 5. So it means that when I get to the n term, this one will be like n minus 1 factorial. So this is n minus 1. 5, 5 minus 1. 4, 4 minus 1. So that's what I'm going to get at the end of the day. And here we are going to assume that our n should be greater than or equal to 1. N is 1. So you can see that when I put 1 here, when n is 1, and when n is 1, I should be able to get this right here. When I put 2 inside here, 2, here 2, and here 2, I should be able to get this. So you can try that and see what we are going to get. So we have a lot of functions and they are n derivative, right? We can have a lot of function with the n derivative. For example, if I have y is equal to e to the power ax, right? Its n derivative will be equal to e to the power an e to the power ax. So that will be the n derivative. How did I see that? Y1 is the same as ax. Y2 is the same as a squared this. Y3 is also the same as y to the power 3, a to the power 3 that. So you can see that when this one is 1, this is 1. When this one is 2, this one is 2. When this one is 3, this one is 3. So when this one is n, this one is also going to be n. So you should be able to know how to do some of the differentiation. Somebody will ask me, how did I do this? This one, I maintain the function, then I differentiate the top, which will be a, right? Then when I come here, when I'm coming to the next, I will do this one again. But when I'm doing this one, it's going to be like a times, then I'll differentiate this times a again. So a times a will be a squared. Then this one will be times a again, a cubed, which is giving us what we have there. Is that right? So we have, a lot of functions that we can differentiate. We can differentiate. The other time I showed you how to differentiate a sine function, right? So a function like sine x ax plus b, when I want to find its nth derivative, this is going to be an sine sine ax plus b plus 2 pi over, no, it should be n because we are getting to the n derivative, n divided by 2 pi. So this is what you are going to get. And remember, I told you how to do it whenever you are doing with a sign, right? So this one, let me just prove this one for you and then we just go. So with this one, this is how I did it. I'll first pick y1. So y1 is going to give us cos ax plus b. Then I need to differentiate what is inside, which is going to give us a. So y1 is going to give us, let me shift this one here small. Y1 is going to give us a cos x plus b. What will be y2? So y2, we are going to differentiate this. But don't forget, always when we are differentiating this, we are going to differentiate what is inside the bracket. So when I differentiate what's inside the bracket, I'll get a again. So this one will become squared. So this one will be a squared. But when I differentiate cos, I'm going to get minus sign. So I'm going to get minus sign, minus. So minus sign ax plus b. Then we can see the pattern. The next one will be minus a to the power 3 cos ax plus b. In that order, I get into the yn. Now what can I do here is, now since the function is in terms of sign, I want to make sure that I write all the functions again in terms of sign, right? So that's what I'm going to do. So I want to write this one in terms of what? I want to write this one in terms of what? In terms of sign, right? So now one pattern that we can see, we can see a to the power 1 going with this, to the power 2 going with this, to the power 3 going with this. So we can see a here, a squared here, we can see a cube here. So automatically this one will be a to the power n. Now I want to write this one in terms of sign, right? I want to write this one too in terms of sign. I want to write this one too in terms of sign. So what we are going to do is we are going to use the trig expansion, a plus b, which is equal to, when I expand this, I get sine a cos b plus cos a sine b. So I'm using this trig to differentiate to expand that. Now here, I'm going to pick the whole of this. I'm going to pick the whole of this to be my a. Then I'll choose b to be something, right? I'll choose b to be something. So the whole of a will be a plus bx, then plus something, right? So when I expand this, I'm going to have sine a plus bx cos what? Cos something plus cos ax plus b sine something. So remember the other video, what we did? We started by picking something, since this one is cos a x plus b, then we need to pick something here, something here, something here. Since we need cos a x plus b, we need to pick something here so that this one will be 1, and pick something here so that this one will be 0. So the only thing that we can pick is we can pick 90, because we know that cos 90 is 0 and sin 90 is 1. So since cos 90 is 0, this one will be 0, which will make everything here 0. Then this one is 1, which will be left with this. So it means that this one can be written as a plus bx plus pi over 2, right here. So that's what we are going to have. Let me go back. So that's what you are going to have, right? And rewrite this one again. So ax plus b plus 1 over 2 pi. That's cos 90. The next thing is we need negative sign of this. So this is the sign, right? So we need to put something here so that this one will give us -1, so that we can get the minus of that, and then put something here so that this one will be 0. And the something that we can put there is pi, and pi. Now we know that pi of this, cos pi is -1 and sin pi is 0. So this one goes to 0, and this one is going to give us the negative of this. It means that we can replace this by this. So this is going to be ax plus. Now pi can be written as 2 over 2 pi. So when you look at the pattern, the next one will be 3 over 2 pi. So when I bring it down, the last one I'm going to have sine ax plus b plus n over 2 pi. So that's the reason why we had what we wrote here. So this is how we had this one. So we use the expansion, and then you just do them randomly to do it. So these are some of the functions that you can find nth derivative of, right? So in the next video, now we can go through the Leibniz theorem. See you in the next video.